Hi everyone, I'm Miss Paws, and last time we talked about how human beings and cats can clearly see nodes and edges in graphs. But we haven't talked about how we convey all that to a computer. Well, as it turns out, there's actually more than one way we can explain this to a computer. Today we're going to talk about two types of graph representations: Adjacency List and Adjacency Matrix. This is part 2 of a 2-part video on graph representations. Make sure to watch the first part if you haven't already, since we will be referencing a lot of the terminology in that video. An adjacency list is a collection of unordered lists used to represent a graph. Let's first talk about an adjacency list for the directed case. We list all our nodes. A goes to B and D. There are no outgoing edges on B. C goes to A, and D goes to B. In an adjacency list, we list only the node pairs for edges that exist. We know that each edge in an undirected graph is bidirectional. Thus, in the undirected case, A goes to B, C, and D. B goes to A and D. C goes to A, and D goes to A and B. In the weighted case, we make sure to include the weights along with the edges. So A goes to B, edge weighted 1, and D, edge weighted 4. There are no outgoing edges on B. C goes to A, edge weighted 8, and D goes to B, edge weighted 5. Now, another type of graph representation is an adjacency matrix, which is a square matrix used to represent a graph. Let's first talk about an adjacency matrix for the directed case. We list all our nodes on the left-hand side going down, and on the top going from left to right. We will place a 1 whenever there's an edge coming from a node on the left side to a node on the top. We will place a 0 when there is no such edge. Since A goes to B and D, in the first row we mark 0, 1, 0, 1. There's a 1 in the B and D columns. Similarly, in the next row we have all zeros since there are no outgoing edges from B. In the next row, we have 1, 0, 0, 0 to represent the edge from C to A. And in the final row, we have 0, 1, 0, 0 to represent the edge from D to B. Note that on the diagonal of the square matrix going from top left-hand corner to bottom right-hand corner is all zeros. They're all zeros because there are no self-loops in this graph. That is, A does not go to A, B does not go to B, etc. In the undirected case, our adjacency matrix looks like 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0. A goes to B, C, and D. B goes to A and D. C goes to A, and D goes to A and B. In the weighted case, we make one minor change. Instead of placing 1 wherever there is an edge, we place the weight so our adjacency matrix looks like 0, 1, 0, 4, 0, 0, 0, 0, 8, 0, 0, 0, 0, 5, 0, 0. Now that we have the basics of adjacency list and adjacency matrix down, let's code it so the computer understands our graph. We are going to do 2 examples here in Python: the undirected case and the weighted directed case. Let's first start out with an adjacency list. We are going to make this in a dictionary of lists. Each key is a node A, B, C, D, and each value is the list of nodes it is adjacent to. We already wrote out what this looks like, so this is what it will look like in code. Let's now do the directed weighted case. As you can see, it's very similar. But just like how we did it before, we are going to have dictionaries inside the list mapping an edge to the weight. Okay, so now on to adjacency matrix. First, let's decide on an ordering. We're going to represent A being the 0th row and 0th column, B being the first row and first column, C being the second, and D being the third. So this is just what we did previously. I'm just not including the letters here because it wouldn't make sense. Just representing each node as a row and column number is great, because then when we are looking for an edge, we can just index into the matrix. For example, if we want to check if there's an edge between B and C, we just look at the first row and second column and see if there's a 1 or 0 there. Our graph will look like a list of lists. I'm going to import NumPy here so we can see our matrix beautifully. It looks just as we had written before. For the directed weighted case, it will look something like this. Now, I'm sure you're thinking, this is all great, Miss Paws, but which one do I use? Well, I'm really glad you asked. We will need to examine the space complexity and time complexity of these two representations. Let's first take a look at space complexity. Our adjacency list has all the vertices and edges listed, so O of number of vertices plus number of edges. The lines by the V and E basically mean the number of vertices and number of edges. Our adjacency matrix is a square matrix where the number of rows and the number of columns is equal to the number of vertices. So that's O of number of vertices times the number of vertices, or number of vertices squared. Let's now revisit the space complexity of adjacency lists, O of number of vertices plus number of edges. This is in terms of two variables, the number of vertices and the number of edges. Can we make this in terms of one variable, in terms of vertices in particular? Well, the number of edges there are depends on the type of graph. If we have a dense graph, remember we said that there are n-1 times n divided by 2 edges, where n is the number of vertices, so we can substitute that with a v. The n square is a dominating term, so we can make it as O of number of vertices squared. So altogether, that's O of number of vertices plus number of vertices squared. Yes, the dominating term is O of v square, but the reason I'm using the full O of v plus v square is to show that the space complexity is a little more for adjacency lists than that of an adjacency matrix, O of v square. For a sparse graph, we had covered in our last video that there are n-1 edges, so the number of edges is on the order of O of v. So altogether that's O of v plus v, which is less than that of an adjacency matrix. Technically that's still O of v. In any case, what we learned here was that when it comes to space complexity, adjacency matrices are more optimal for dense graphs and adjacency lists are more optimal for sparse graphs. Okay, but that's only one part of our analysis. Now let's analyze time complexity. For an adjacency list, if we want to visit all neighbors of vertex A, which is a vocab word that means all the vertices a particular vertex is connected to through an edge, the time complexity is O of number of edges of a given vertex. We go to A and see all the neighbors of A, B, C, and D. If we want to see if an edge exists between two vertices, say if there is an edge between B and C, we can find B and then iterate through each edge from B to see if there is an edge to C. So that's O of number of edges of a vertex. For an adjacency matrix, if we want to visit all neighbors of vertex A, that's O of v. We go through each vertex and check if there's a 1 to see if it's a neighbor of A. To find an edge, that's O of 1, because we can just check the row for B and column for C, and find if there's a 0 or 1. So, what does that mean? If we're visiting all neighbors of a vertex, adjacency list is faster because it is O of edges of a vertex, which will always be less than O of v. If we want to check if there's an edge between two vertices, an adjacency matrix is always faster because it is O of 1. As it turns out, we are usually visiting all neighbors of a vertex, so the adjacency list is what we will be using most of the time during graph traversal. If we are working with very dense graphs, we may choose to use an adjacency matrix because it has a better space complexity. But in all our examples, we will stick to adjacency lists. Okay, so one last lingering question. Now knowing what we know about time complexity, you might think, why use an adjacency list and not an adjacency set? Visiting all neighbors would have the same time complexity, but finding if an edge exists would be much faster with O of 1 on average. Well, first of all, great question. Second of all, finding if an edge exists is not something we normally do during graph traversal, so optimizing that doesn't really matter. If finding if an edge exists is so important to us, we should use the adjacency matrix because it would be faster. The time complexity is O of 1 always, not O of 1 on average. Also, it is slightly faster to traverse lists rather than sets, and since visiting all our neighbors is what we will do mostly in graph traversal algorithms, we will stick to using adjacency lists. So that's all. Hopefully, you are not confused. Now we are ready to get our paws dirty and learn some graph traversal algorithms. See you soon!